NEC Article 250.66 addresses the sizing of the grounding electrode conductor, or GEC, to ground rod. This section of the code states that the GEC to rod, pipe, or plate electrode shall not be required to be larger than 6 American wire gauge copper wire or 4 American wire gauge aluminum wire. The phrase "shall not be required" is key to understanding how this rule is applied in practice. This means the authority having jurisdiction, or AUJ, cannot mandate the use of a GEC larger than these specified sizes when connecting to a 5/8 inch by 8 foot ground rod. However, this does not restrict an engineer of record from specifying a larger GEC if they deem it necessary for a particular installation. The limitation on GEC size for smaller ground rods such as the 5/8 inch by 8 foot size is related to the rod's ability to dissipate fault current. A larger conductor would not significantly improve the rod's performance in dissipating fault current into the earth because the rod is the limiting factor. The term "shall not be required" applies to both the AHJ and the engineer of record, but in different ways. The AHJ cannot require a GEC larger than 6 American wire gauge copper or 4 American wire gauge aluminum for a 5/8 inch by 8 foot rod. The engineer of record, however, retains the discretion to specify a larger size if they believe it is necessary for the specific installation, taking into account factors like potential fault current levels, soil conditions, and the overall design of the grounding system. The engineer might specify a larger conductor to provide a greater margin of safety or to meet specific performance requirements beyond the minimum code requirements. If an engineer specifies a 3/4 inch by 10 foot rod with, say, number 2 American wire gauge, the specification is potentially enforceable depending on the context and the engineer's justification. A larger rod might offer improved grounding performance compared to a 5/8 inch by 8 foot rod, particularly in terms of fault current dissipation and impedance to ground. The engineer's specification should be based on a thorough evaluation of the site-specific conditions and the electrical system's needs. The AHJ will typically defer to the engineer's judgment as long as it is technically sound and consistent with good engineering practices. In summary, while the NEC sets a minimum standard for GEC size based on the type and size of the grounding electrode, it allows for engineering judgment to dictate the use of larger conductors where warranted. The phrase "shall not be required" provides flexibility while ensuring a baseline level of safety. The decision to use a larger GEC should be based on a comprehensive assessment of the electrical system and the specific requirements of the installation. Considerations for the selection of a grounding electrode conductor GEC include: firstly, the size of the grounding electrode. As mentioned, the NEC specifies that for rod, pipe, and plate electrodes, the grounding electrode conductor GEC does not need to be larger than 6 American wire gauge copper or 4 American wire gauge aluminum. This is outlined in NEC section 250.66a. However, this requirement is specifically for these types of electrodes and doesn't necessarily apply to other types of grounding electrodes, such as concrete encased electrodes or ground rings. Secondly, the size of the service entrance conductors. For systems where the grounding electrode conductor GEC is connected to the grounded service conductor, the size of the service entrance conductors plays a crucial role. According to NEC section 250.66, the size of the GEC must not be less than what is specified in table 250.66, which is based on the size of the service entrance conductors. This ensures that the GEC is adequately sized to handle potential fault currents. Thirdly, the material of the grounding electrode conductor. The NEC recognizes both copper and aluminum as acceptable materials for grounding electrode conductors GEC. The choice between copper and aluminum often depends on factors such as cost, availability, and environmental conditions. However, it's important to note that the ampacity of aluminum conductors is generally lower than that of copper conductors of the same size, so a larger size aluminum conductor may be required to achieve the same level of performance. Fourthly, the type of grounding electrode. The NEC recognizes various types of grounding electrodes, including rod, pipe, and plate electrodes, concrete encased electrodes, and ground rings. Selection of the appropriate grounding electrode depends on factors such as soil conditions, available space, and local requirements. Each type of grounding electrode has its own specific requirements for installation and sizing of the grounding electrode conductor GEC. Fifthly, the number of grounding electrodes. In some cases, it may be necessary to install multiple grounding electrodes to achieve the desired level of grounding performance. When multiple grounding electrodes are used, they must be bonded together to form a grounding electrode system. The size of the bonding jumper used to connect the grounding electrodes must be in accordance with NEC section 250.66. Sixthly, the location of the grounding electrode. The location of the grounding electrode can also impact the selection of the appropriate size of the grounding electrode conductor GEC. For example, if the grounding electrode is located a significant distance from the service equipment, a larger size conductor may be required to minimize voltage drop. Additionally, the NEC requires that grounding electrodes be located as close as practicable to the service equipment. Seventhly, the soil conditions. The soil conditions at the site can significantly impact the effectiveness of the grounding electrode. Factors such as soil resistivity, moisture content, and temperature can all affect the ability of the grounding electrode to dissipate fault current. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or use a ground-enhancing material to improve grounding performance. Eighthly, the local requirements. Local codes and regulations may impose additional requirements for grounding electrode conductors GEC beyond those specified in the NEC. It's important to consult with the local authority having jurisdiction AHJ to ensure compliance with all applicable requirements. Ninthly, the potential fault current. The potential fault current at the site is a critical factor in determining the appropriate size of the grounding electrode conductor GEC. The GEC must be sized to safely carry the maximum available fault current without overheating or causing damage to the conductor or surrounding equipment. Consulting engineering studies might be required to determine the available fault current at the service equipment. Tenthly, the environmental conditions. The environmental conditions at the site, such as temperature, humidity, and exposure to corrosive substances, can also impact the selection of the appropriate size and type of grounding electrode conductor GEC. In harsh environments, it may be necessary to use a corrosion-resistant conductor or provide additional protection to prevent premature failure. In addition to these considerations, it's also important to ensure that the grounding electrode conductor GEC is properly installed and maintained. The NEC provides detailed requirements for the installation of grounding electrode conductors GEC, including requirements for bonding, terminations, and protection from physical damage. Regular inspection and testing of the grounding system can help to ensure that it is functioning properly and providing adequate protection against electrical faults. Regarding ground rods and specifically what size is sufficient, the NEC provides guidelines but doesn't explicitly dictate a single best size. The most common size encountered is 5/8 inch in diameter and 8 feet long, but factors like soil resistivity and local regulations influence the optimal choice. Here is a breakdown of factors to consider. Firstly, the NEC minimum requirements. The NEC, specifically section 250.52 of FIV, requires that ground rods be at least 8 feet long and made of certain materials such as galvanized steel or copper. It doesn't specify a minimum diameter, but common practice and UL listing standards have established 5/8 inch as a widely accepted size. Secondly, soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Low resistivity means better conductivity. In areas with high soil resistivity, a single ground rod might not provide sufficiently low resistance to ground. In such cases, multiple ground rods are often required, spaced at least 6 feet apart. The 3/4 inch or larger diameter ground rods are also sometimes used to achieve lower resistance in high resistivity soils. Thirdly, local amendments. Local jurisdictions can amend the NEC to include more stringent requirements. Some areas may require larger diameter ground rods or other grounding enhancements due to specific soil conditions or other factors. It's always important to check with the local authority having jurisdiction AHJ to determine if there are any local amendments to the NEC that apply to grounding requirements. Fourthly, the desired resistance to ground. The NEC doesn't specify maximum resistance to ground for a single ground rod. However, Section 250.53 APWA states that if a single rod, pipe, or plate electrode doesn't achieve a resistance to ground of 25 ohms or less, an additional electrode must be installed. The 25 ohms limit is a common benchmark for grounding system performance. In some cases, engineers may design grounding systems with a lower target resistance to ground to provide enhanced protection for sensitive equipment. Fifthly, the fault current considerations. The size of the ground rod also plays a role in its ability to handle fault current. A larger diameter rod has a greater surface area in contact with the soil, which allows it to dissipate fault current more effectively. In applications where high fault currents are anticipated, a larger diameter ground rod may be necessary to ensure that the grounding system can safely handle the fault current. Sixthly, the mechanical strength. While electrical performance is the primary consideration, the mechanical strength of the ground rod is also important. A larger diameter rod is generally more resistant to bending and damage during installation. This can be particularly important in rocky or difficult soil conditions. Seventhly, the corrosion resistance. Ground rods are typically made of galvanized steel or copper. Galvanized steel is a cost-effective option, but it can corrode over time, especially in acidic soils. Copper ground rods are more resistant to corrosion, but they are also more expensive. The choice between galvanized steel and copper depends on the soil conditions and the desired lifespan of the grounding system. Eighthly, the ease of installation. The ease of installation is another factor to consider when selecting a ground rod. Smaller diameter rods are generally easier to drive into the ground, especially in hard or rocky soils. Larger diameter rods may require specialized driving equipment. Ninthly, the cost. The cost of the ground rod is also a consideration. Larger diameter rods are generally more expensive than smaller diameter rods. The overall cost of the grounding system should be considered in the context of the performance and reliability requirements. Tenthly, the UL listing. Ground rods should be UL listed to ensure that they meet industry standards for safety and performance. UL listing indicates that the ground rod has been tested and certified to meet specific requirements for dimensions, materials, and electrical performance. In practice, a 5/8" by 8-foot ground rod is often sufficient for residential and light commercial applications where soil resistivity is reasonably low. However, in areas with high soil resistivity or where a lower resistance to ground is desired, multiple ground rods or larger diameter rods may be necessary. A qualified electrician or electrical engineer can perform soil resistivity testing and recommend the appropriate grounding system for a specific application. Now, to elaborate on the function of a ground rod. A ground rod serves a critical role in electrical safety by providing a low impedance path for fault current to return to the source. This low impedance path helps to quickly trip the circuit breaker or fuse, interrupting the flow of electricity and preventing electrical shock or fire hazards. Ground rods work by dissipating electrical current into the earth. When a fault occurs, such as a short circuit between a live wire and a grounded metal enclosure, the fault current flows through the grounding system, including the ground rod, and into the earth. The earth acts as a conductor, allowing the current to return to the source, which is typically the electrical transformer. The effectiveness of a ground rod depends on several factors, including the soil resistivity, the depth and diameter of the rod, and the presence of other grounding electrodes. Soil resistivity is a measure of how well the soil conducts electricity. Lower resistivity means better conductivity. In areas with high soil resistivity, a single ground rod may not provide sufficiently low resistance to ground, so multiple ground rods are often required. The depth and diameter of the ground rod also affect its performance. A deeper rod generally has a low resistance to ground because it is in contact with more soil. A larger diameter rod has a greater surface area in contact with the soil, which allows it to dissipate fault current more effectively. The presence of other grounding electrodes, such as metal water pipes or building steel, can also improve the overall grounding system performance. These electrodes should be bonded together to form a grounding electrode system. In addition to providing a path for fault current, ground rods also help to stabilize the voltage potential of the electrical system with respect to the earth. This helps to reduce the risk of electrical shock and prevent damage to sensitive electronic equipment. Ground rods are typically installed by driving them into the ground until they are buried to their full length. The top of the rod is then connected to the Grounding Electrode Conductor GEC, which runs back to the service equipment. The connection between the ground rod and the GEC must be made with a listed connector that is suitable for direct burial. It's important to note that ground rods are not a substitute for proper wiring practices and other current protection. They are just one component of a comprehensive electrical safety system. Proper wiring practices, such as using the correct wire size and making secure connections, are essential for preventing electrical faults. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of electricity in the event of a fault, protecting people and equipment from harm. Regular inspection and testing of the grounding system can help to ensure that it is functioning properly. Ground resistance testing can be used to measure the resistance of the grounding electrode to ground. This test involves injecting a small amount of current into the ground and measuring the voltage drop. The resistance is then calculated using Ohm's law. If the ground resistance is too high, additional grounding electrodes may be required to improve grounding performance. Visual inspection of the grounding system can also help to identify potential problems, such as loose connections, corroded conductors, or damaged ground rods. Any problems should be corrected promptly to maintain the integrity of the grounding system.